This is the entertaining part of our two-day workshop format. For those of you who haven't seen us do this before, it's kind of like a speed dating process. Each of these guys have used an extensive sorting algorithm to line up alphabetically by last name. And hopefully the slides that are at the back match the speaker. And literally it'll be about 60 to 90-second speaker coming up here giving you an overview of what their poster is, so you can put a subject to a name to a face and go and seek them out during the reception, as well as the demo tables that are out there. So please hold applause and all that stuff. It's just a quick commercial for all of the speakers that are coming up. And for you.
Wow, service. Service with a smile. My name is Derek Atkins, Chief Technology Officer at SecureF Corporation. Our core technology is a future-proof, quantum-resistant public key operations. For RISC-V, what we've done is we actually partnered with a bunch of people who you've also already heard from. What we've done is built a secure boot solution using our quantum-resistant signature algorithm, which gets a tremendous speed improvement over existing technologies. We have a demonstration using Minute and on the Hi5 platform, so you can come see our secure boot solution. We can show you how fast it is compared to other technologies. So come by and talk to us. We already partner with lots of people. We can partner with you too.
Hi, I'm Mary. Jie Chen is an open source free software framework and toolkit for generating assemblers, disassemblers, simulators, and test suites, all using a single definition of an architecture. From this description, tables are generated in nib opcodes from which the GNU assembler can be generated, and a disassembler for obstump and GDB. Jie Chen has been generated over the past 20 years, or developed over the past 20 years, and is used by many GNU toolchains. In my poster, I hope to describe this in more detail, as well as how Jie Chen generates an ISA compliance test suite, and how the simulator can be run in lockstep with the actual silicon chip design to verify the implementation. Thank you.
So good evening, everyone. My name is Cristian Palmiero. I work for Qualcomm. I'm here with my master's thesis supervisor, Professor Luca Carloni from Columbia University. So we designed and implemented a low overhead protection scheme based on dynamic information flow tracking for RISC-V cores. So the goal of the project is to protect IoT applications from memory corruption attacks. So what is DIFT, Dynamic Information Flow Tracking? So DIFT is a very promising technique for software security. It's based on tags, so each data item is extended by an additional field called tag that identifies whether a data item is spurious or authentic. It's based on tag initialization, where spurious data items are identified, tag propagation, where dependencies are tracked, and tag check, where restrictions on spurious values are applied. So the target platform we have chosen for our project is RISC-V, that is a 32-bit RISC-V core designed by ETH Zurich and Università di Bologna. It's part of the PULP platform. So we created the tag infrastructure. We designed the additional logic related to tag initialization, propagation, and check. We crafted a security policy that allows the core to be protected against memory corruption attacks. Finally, we synthesized our design into a FPGA, and we demonstrated the effectiveness of our scheme, and we showed that our design does not incur in any latency overhead and has a negligible area and power overhead. Thank you.
Hi, my name is Andrew. Short company introduction. Syntacor is an IP company. We specialize in RISC-V IP. We provide our initial line of course, provided with full collateral, documentation, tests, and of course compiler support. We also provide workload-specific customization for our cores, which can yield substantial improvements in performance and power efficiency. Our SCR1 core has been released under permissive SHL license in May 2017, and we maintain our best effort to keep our core updated as the specifications make progress. So you can see all the basic characteristics on the slide. I won't go into the details. SCR1 has been used over the course of last year and in some commercial applications, as well as academia and educational projects. Over the course of 1 year, we have collected some feedback, some experience from customers using our core, and we have created a user manual quick start style guide, which describes which has some advanced tips for those who want to customize our core. And we have a stand with poster with demos, which you can see on the slide. So welcome to our demo stand for these demos. Thank you.
Hi, so I'm Alex Bradbury. I'm co-founder and director of Low Risk, which is a not-for-profit which is aiming to support and help grow the open source hardware ecosystem. One thing many of you know I've been working on for a while is the RISC-V backend for LLVM. I'm upstream code owner and primary author. I have a poster talking about the current status, the approach I'm taking, next steps, adding your own extensions. Some of you might have seen my tutorial delivered yesterday. If you'd like to find out more or get involved, come and talk to me. I'm especially interested if you have things in downstream ports that you'd like to get upstream. I can help talk you through the best way of doing that. Thank you.
Hello everyone, I'm Jie. Today I will introduce you our research in about the instruction cache hierarchy in the multi-core system, which based on the Power platform. Here is the typical clusters in Power platform, which use the private instruction cache to have a minimum instruction access cycle, but the data duplications and miss penalties are the major drawbacks for this system, so which lead to degraded performance and area and energy performance. So to solve this, in the previous work, 2 models was proposed. The first one is the SP single port shared instruction IGASH, which uses a crossbar between cores and the shared IGASH. Here is the details of the shared IGASH. We can see there are 3 main components. First, text, data, and IGASH controller, which can be different for different designs. And the next one is the MP, which use multiple read port shared IGASH. Both of them achieved good results compared with the private instruction IGASH. But in the real practice of the GreenWave Technologies application IoT processor, GAP8, and the PARP tester chip, WOLF, we found that they suffered from timing issues from the backend. So it is hard for backend to do the timing converging. So a new 2-level timing relaxing and energy efficiency instruction cache was proposed. Here we combine the private IGASH and the shared IGASH together. So we have the synthesis and power estimation. Finally, we have achieved a good result. Here is the result of the comparison between among SP, MP, and 2-level IGASH. We can see for the performance, the throughput, we decrease 15%, but for the total power efficiency, we increase about up to 50%. And for the view of the global cluster, we achieved 10% for the power efficiency. And this architecture will be fabricated with 22 nanometer global foundries technologies soon. Thank you.
Hello, I'm Matt Cockrell, a senior engineer with Google, and I'll be hosting a poster session describing our verification of Palpino's risky core using Sting, an instruction generator tool. We'll describe a use case within Google of using the risky core as a job scheduling and dispatch mechanism. We'll walk through the flow of doing the verification as well as the flow of addressing any bugs or issues found along the way. We'll also be sharing the results where we found more than 30 RTL, documentation, and toolchain issues. Sting tests were found to have covered most of the core functionality, so we'll have some core coverage results as well. And areas with low coverage were addressed with test stimulus and adjustments and regressions runs later. Thanks.
Good afternoon, everybody. I'm Alberto. I'm presenting a way to co-simulate your unmodified code and your HDL design. So basically, you can run your unmodified code on the QEMU RISC-V emulator, and then using the foreign language interface, interconnect it directly with your logical simulator. And basically, the good news is that you can adapt this approach with whatever bus functional model you have. We have several demos from a UVVM project. And then there, for example, you can run two unmodified Linux instances on two different QEMU interfaces and make them talk together with a logical simulator of your unmodified HDL bus interface. That's it. If you have questions, the code is available, and stop by my poster. Thank you.
Hello, I'm Christian Fabre from CA back in France. So I'm presenting the work done by several students on approximate computing. So why approximate computing? If you can save some bits in computation, you can save energy in the processor. So we have developed a framework to explore with that. Basically, there is a set of new instructions, a global set of the processor which deals with the approximation, and the tool set which goes for the exploration with. So we build on the RISC infrastructure, not only the instruction set, of course, but also the simulators which go with that. There is some we have added some pragma to the C language, so to turn the floating point into fixed point and then to apply to that the approximate computing into the processor. The toolchain allows to provide some figures in terms of energy savings, and it's based on a standard that we can find on benchmark we can find in the literature. So you come back to the poster, and we can go into more details. Thank you.
Hello everyone, my name is Juan Fumero. I'm a postdoc at the University of Manchester. What we present here is how to enable RISC-V support on the Maxim virtual machine. So in one sentence, I have to summarize, what we do is how to compile at runtime Java programs in order to be executed on the RISC-V architecture. To do so, we base on existing virtual machine. It's called Maxim VM. And Maxim VM is a research project that started a few years ago in the Oracle Labs, and we took it at the University of Manchester to do our research. So apart from the RISC-V backend, we have other ports for Intel, for ARMv8, and for the GPU. I'm actually in charge of the GPU backend, so you can ask me later if you want. So basically, what Maxim is a meta-circular virtual machine. What does it mean? It's a Java virtual machine written in Java. It has a couple of JIT compilers, C1x and T1x. You can ask me later for more details. Multiple garbage collection algorithm, And this is nice because you can prototype your compiler and all your algorithms in Java using your existing IDE, Eclipse, NetBeans, profilers, and so on. So if you want to know more details about the current status of RISC-V, please come along and I will tell you much more detail how it's executed, how it's run, how it's checked, etc. Thank you.
Good afternoon, and my name is Hayu from Dolphin Integration, a French company located in Grenoble. And today I will introduce you an open platform introduced by Dolphin Integration, which is used for energy-efficient SoC construction based on RISC-V core. And this is a block diagram to show the hardware platform. And the Tornado platform has been designed as a full configurable MCU subsystems, and it is fully configurable and with the standard AMBA interfaces, HB and APB. And it includes a rich set of software libraries, low-level software drivers for the peripherals, and the part of RTOS operating system. And apart from the hardware platform, we will introduce a tool, an innovative tool, which is used for the power-aware software development, and along with the advanced debug capabilities open to RISC-V architecture. And it is able to estimate the power consumption during the software execution, and which is used to optimize the software program and your SoC architecture. And it provides also the open APIs used to create and import the simulation models for the SoC in construction. So lastly, this tool can be downloaded on our website for free. Thank you very much.
Hi everybody, I'm Zdenek, I'm from Codasip, and well, what we do? Well, we provide IP, soft core RISC-V IPs. We have a quite rich portfolio of those IPs, so you can choose really small, 0, pipeline stage core, 3-stage, 5-stage, 7-stage, it's up to you. You can also choose which part of ISA you would like to have there, so you can have just really basic ISA, or you can have IMC or IMF, it's up to you. But not only that, we allow you to add your secret sauce, either in a form of microarchitecture tweak or in a form of instructions and extension. In any case, you describe the secret sauce in a C-like language, and then we are able to generate the new SDK and HDK. So you're going to obtain a C compiler that is aware of new instructions, assembler and so. And you can also obtain the Verilog code or VHDL code or your VM environment, verification environment that is aware of your secret sauce. So recently, we have released a new generation of a studio. That's a tool that generates the SDK and HDK. So there are quite new features there, such as 2-var JTAG or new LLVM. We are working on 6 right now. Or we support a native AMBA interface, so no need for any bridges between anything you have in your chip. So if you would like to differentiate, if you would like to have your solution that's better than your competitor, just to buy and we can have a talk. Thank you.
Hello everybody, I'm Felix Kaiser from the Computer Architecture Group at the University of Heidelberg, and we developed a floating point unit, and therefore we needed a verification environment. We implemented it with SpecMan-E and the universal verification methodology. SpecMan-E is a hardware verification language, and UVM is the industry standard for simulation-based verification environments. Therefore, we needed a known good and error-free reference model. We decided to take the Intel processor and extract the floating point instruction it performs. our developed reference model looked like this. We could interface with the E language with the C over the function level interface. And in the C code, we needed to use the Intel intrinsics to make sure that the actual operations we wanted to are used and that the compiler won't optimize them out. If you're interested in this topic, please visit me at my poster at the session later.
Hello, everybody. My name is Aleksandar Kamkin. I'm from Institute for System Programming of the Russian Academy of Sciences. And I'd like to present a microtask for RISC-V, which is open source, flexible test program generator for RISC-V microprocessors. Actually, microtask stands for Microprocessor Testing and Specification Toolkit, that the framework which were used to develop test program generator. And generator itself consists of two parts. First of all, architecture-specific part called model, which is constructed automatically from ISA specifications. And the second part is architecture-independent generation core, which implements some general testing techniques like randomization, constraint solving, and like. So input is test template in Ruby-based domain-specific language, which specify how to compose complex instruction sequences from simple ones, describe test data constraints and probability distributions. So what we have done, we have formalized more than 200 instructions. And here you can see how ISA specifications look like. So we have instructions, we have registers, we have addressing modes. So we can specify assembly syntax, binary encoding actions, and so on. And this is an example of test template in Ruby language. So we can compose complex sequence from simple ones, describe constraints and probability distributions. So for more information, please visit our poster. Thank you.
So, hello, my name is Luke Layton. I'm here to present the Libra RISC-V processor and invite people who would like to participate. So, why Libra? Well, if there's anybody here from the NSA who would like to have a backdoor coprocessor in the Libra RISC-V core, please see me afterwards, and just bear in mind that I will need to publish the RSA private and public keys on the internet. There are several parts to this that are needed. A GPU. Now we may be licensing Vivant GC800, which is $250,000 to license. So if there's anybody who would like to do a RISC-V based GPU, 150 megapixels a second, 30 million triangles a second, and 5 gigaflops, I can put that to the anonymous sponsor as a bid on your behalf. We also need to do video 1080p 60. So again, there is an opportunity if anybody would like to think. Now, everything has to be Libra licensed because it has to be audited for security reasons by the Indian government. So I'd also like to thank the following people for providing RTL over the past 15 years. Richard Hervé for the RGB-TTL RGB-TTL court, that if anybody wants to use that, it's BSD licensed. It'll save you about $50,000 on licensing costs. I'd also like to thank Alex Bradbury from Low Risk. They have found a gigabit RGM2 RTL, which again saves anybody who wants to use that $50,000. And especially I'd like to thank Clifford and Edward from Symbiotic for the USB 3 and the DDR3 PHY, which we're talking about, because those save people $500,000 each. The last part is we're working on a PinMux, which is interestingly is one piece that is missing from free software environments. I'd very much like to talk to Sci5 to include the IOF code in this, so that it can empower you to achieve the dial-a-chip thing that you very much want to do. So, thank you very much.
Hello everyone, I am Heng Lin. I am a graduate student from Tsinghua University, Hsinchu, Taiwan. This work is cooperate with NDs. This work is entitled Enable ROS Flow and Framework for RISC-V Architectures. There are many famous ROS projects, such as Server, Redux, ManSafe. They are cover many fields, such as OS and website engines. So the item we work on is as follows. There are 3 for ROS running on RISC-V platform. There are ROS support on Linux and ROS on bare metal with and without standard library. In ROS compiler flow, the ROS front end first translate ROS code into LLVM IR, and LLVM will compile IR into RISC-V assembly, and then the linker will link the related libraries. To enable thread on bare metal, our thread library can create schedule to allocate thread while performing content switch. We store the thread information into memory and load the other thread informations. In our research, we found LLVM compiler can generate factor instruction in x86 target. But however, the same IR code in RISC-V, it cannot. Ongoing work, we want to design, we want to implement the factor instruction or packaging D in RISC-V to ROS. Thank you.
Hello, my name is Maja Malenko. I'm a PhD student at Graz University of Technology in Austria. My poster is about a co-designed hardware-software platform with some hardware-based extensions. So the platform I'm working with is a Vscale-based microcontroller with some on-chip peripherals like the UART and GPIO. We started using Vscale because the group I'm working in used Vscale like 3 years ago. So there wasn't a lot of choice about using implementation, so I just continued using Vscale. I know that now it's deprecated, but we have updated according to the newest specification. And then on top of it, we ported our own operating system. It's called MC Smart OS. So it's a real-time kernel with preemptive and prioritized tasks. And also, we developed a MPU, memory protection unit, which separates the code, the stack, and the data region of the tasks, as well as some API functions. So it's a basic MPU. We have designed it according to the PMP, physical memory protection model of RISC-V, but then on top of it, we have extended it with 2 registers. We wanted like a lightweight way of protecting shared resources, including peripherals, which are memory mapped, and then some shared memory for inter-task communication. So that's why we used another additional 2 CSR registers, which are bit-filled registers, and they can protect, one of them protects up to 32 peripherals, and then the other one is used for protecting shared memory for communication between tasks. So this is a very lightweight form of protecting the shared resources. Lightweight in order of hardware resources, also memory that is used, and also it doesn't impose any overhead during context switch time. So if you want more information about the way it's implemented, you can visit my poster. Thank you.
Good afternoon, everyone. I'm Leslie Shannon, and I'm here to present on behalf of some student work done by a graduate student and undergraduate student, Eric Matthews and Patrick Aguila. We're announcing a new soft processor that's customized for FPGA Fabric. It's called Taiga. It's highly configurable, and the key thing about this particular soft processor is that it supports out-of-order execution and early commits. This is extremely important for us as we're interested in heterogeneous system research. If you have a fixed pipeline, tight integration of accelerator instructions automatically causes poor performance. So if you look, you'll see that we've decoupled the different stages. The architecture allows you to actually replicate functional units. So if you have high latency with high initiation interval instructions, you're actually able to replicate those units. We support TLBs, MMUs, scratch pads, caches, and branch predictors. Other than that, I guess I'd really like to point out that this architecture is being scaled to multi-core. If we look at some platform comparisons, if we're looking at multi-core configurations and looking at the idea of, okay, what's a single core in a Rocket or a Leon look like compared to Taiga, you'll see our operating frequency is considerably higher compared to the existing ones with quite a few fewer slices. This device is open source and does run on both Intel and Xilinx devices. We have also compared it in a configuration where we haven't included caches but scratch pads compared to Pico RV, which has no cache support and no scratch memory. Pico RV does run at a higher frequency with fewer resources, but it has a much lower IPC than us. The latest Orca release does not publicly have caches, but does have a branch predictor. It's about the same size as Taiga and has similar IPC as our fixed design. Allowing early commit does get us up to 28% increase in IPC, so it's not insignificant to have that kind of support. Finally, we've also looked at the VEX RISC-V. It's similar in size and frequency to Taiga, and it also has cache support, but it does not support multi-way caches, unlike us. So if you're interested in having this particular processor as an option for whatever you'd like to do, it's fully open source. Check it out at GitLab or come talk to me at my poster. Thank you.
Hello, my name is Paulo. I work for Linky Tools. So have you ever had a piece of code in front of you, assembly code, and you've wondered, is it possible to improve on this? By improve, I mean make it smaller, faster, lower energy consumption. So this is the kind of question that is answered by a super optimizer. If the question is yes, it is possible, then the super optimizer will search for that golden program. So at Linky Tools, we have developed S10. S10 is a super optimization framework. It is retargetable, which means that it's very easy to develop a new backend, front-end for the framework. It's extensible, meaning you can easily develop new algorithms for it, and it's also distributed. It's a very CPU-intensive application, and you can easily distribute it not only throughout many cores, but also throughout many machines. We chose RISC-V to be the first port for S10. We have fully implemented RV32i super optimization with the M extension. We're currently working throughout the other extensions and other architectures like ARM and Intel. And if you are interested in this kind of technology, if you want to know more about S10, its implementation and features, etc., please come talk to me at the poster session. Thank you very much.
Good afternoon, everybody. I'm Lucas Moraes, graduate student from the University of São Paulo, and I'm going to briefly talk about hardware-assisted test scheduling on Linux-enabled multi-core rocket ship. So the basic idea here is to port a certain programming model to rocket ship, and this programming model is called test scheduling, and it's supported by industry standards like OpenMP 4.0. And its basic idea is to enable a test scheduling compliant system to schedule units of computation automatically to available cores while respecting their data dependencies. And these data dependencies are inferred at runtime. And of course, this automatic inference of data dependencies doesn't come for free. So for the most fine-grained workloads, which are workloads for which tasks are very short, the overhead could be too much, right? So some people have already tried accelerating these systems with FPGA acceleration, and they met some success, but the high CPU FPGA communication latencies prevented these solutions from performing as well for the most taxing workloads. So our idea for circumventing this problem would be to basically embed one of these specialized scheduling modules to a multi-core rocket ship, so that we could avoid these excessive communication latencies and get overall better results. And this is an ongoing project. We should have our first working prototype before July. And as an additional thing, the nice thing about this project is that we would like to make releases based on Docker images, apart of making all code available on GitHub so that people may find an environment instantiated all necessary dependencies at the right versions so that things can be reused in the easiest manner possible. Thank you.
Hello, everyone. This long-titled work builds on the huge and influential railroad traced by the PULP project developed by University of Bologna and ETH Zurich. We are Sapienza University of Rome, and we focused on the Palpino microcontroller architecture. We developed a family of new cores for the Palpino architecture, targeting FPGA implementation in the view of exploring microprocessor reconfigurability, adaptive microprocessors. We name our cores S0, T0, T1, F1. S0 is a very baseline core, resembling the micro-risky core, for those who are familiar with it. T0 is itself a family of cores, in that it is a parameterized design. It introduces a form of multi-threading by having multiple program counters in the same core and interleaving the hearts, a small number of hearts in the pipeline. T1 is going to introduce a reconfigurable scratchpad memory subsystem and reconfigurable acceleration units, while F1 is going to address fault tolerance for space applications. The poster focuses on the publicly available T0 cores. These are some facts and figures that we can go through if you come to our poster. Here I will only mention the possibility of the support of inter-heart software interrupts, possibility of suspending individual hearts or the entire core, and the support, partial support of atomic operations for thread synchronization. Thank you. Thank you very much.
Hello. My name is Aleksandar Pajkanovic, and I'm starting a course. For undergraduates in VLSI at the Faculty of Electrical Engineering in Banja Luka, where I teach, that features Chisel. I'm inviting, of course, anyone interested in Chisel education to collaborate on teaching materials. The first programming language learned shapes how one thinks. So introducing Chisel to undergraduates at our school will mean, of course, learning from the start to think at a higher level of describing hardware instead of low-level details. I believe it will be a steeper learning curve, but it will give an edge to these engineers in the context of project development under the umbrella of RISC-V ecosystem. Rocket chip adoption rests upon Chisel adoption. With collaboration in the community, I really hope that we can collect best practices for teaching Chisel and thereby accelerate the adoption of rocket chip code. Rocket chip, of course, uptake will also increase if the code style becomes easier to learn. The idea is to add some kind of extra hand-holding on the exact issues that people have faced. There's, of course, excellent documentation in the Chisel Wiki, Chisel Tutorial, and Generator Bootcamp repositories. So what we would like to add is this description and further details on exact issues, line by line, of the code that people have faced, thus creating a bridge from where the current teaching materials leave off to the more advanced coding techniques such as cake pattern and diplomacy. We do this through something we call Learning Journey, so you can access it via this link. And it is developed in collaboration with Intensivate. I would also like to express special thank you to this company that is actually working to create an accelerator card for scale-out workloads and is investing in the RISC-V community through the Chisel Learning Journey. So, I just wanted to say that the first lecture was held last week, and in the next 2 days we have a workshop in Belgrade with about 30 faculty members who will take part from different 5 universities from Serbia and Bosnia and Herzegovina. So I would like to invite you to join me at the poster session to discuss any possible collaboration. Thank you.
Hello, everyone. My name is Matheus Ogleari. I'm a storage architecture intern, and today I am presenting on behalf of my colleague, Atish Patra, who unfortunately could not be here today. So this work is titled Hot Plug CPUs in RISC-V. So the idea here is that we want to be able to enable and disable RISC-V CPU cores. This underlying idea is not new. This has been done, with PowerPC and Spark for dynamic resource configuration, and also more recently for power management. So we want to be able to enable or disable these cores without having to interrupt the system or physically remove them. So now this is what we do for RISC-V. So how do we do this? This here is our flow for how we take a CPU offline. The first thing we have to do is migrate whatever tasks the target CPU to other CPUs. Then we notify the relevant subsystems that the CPU is no longer there. We update the CPU maps to reflect this change of disabling the CPUs. We have to migrate any interrupts bound for the target CPU to other CPUs. We have to mark the death of the CPU in the scheduler. And finally, we have to move the CPU into a low power idle state. So how do we do it in RISC-V? This is divided into 3 parts as shown in this diagram: user space, kernel, and architecture. The user space, say we want to take a core offline or online. We first we send this command to the CPU hot plug core in the kernel. And that core will talk to whatever subsystems to notify of this change, to either remove or add the CPU. And then this CPU hot plug core will also send signals to the underlying architecture, which will be able to see, hey, we're bringing a CPU online or we're taking it offline. And of course, we have an interrupt handler, which will wait for any further interrupts in case we want to boot back up a CPU that we already disabled. So, thank you.
Hello, good morning, everybody. I hope you enjoy the election of the fastest speech today. My name is Daniel Borgrave. I'm not the guy who needed to talk first, so I will be quick. Basically, Valtrix is an Indian startup. We have developed a tool named Sting, and the real goal of the tool is to create an executable with all the kernels, the tests, the libraries, and all the driver or all the IP on the system on chip. And make an executable so you can run the test live under the device of the test. It can be from FPGA, on your verification system, on emulation, or on the real system on chip. Okay? So because the presenter has not come to Barcelona today, there will be no demo tonight at the session. But you can go and see me and talk about the Valtrix and Sting. And I would encourage you to see the presentation of Google, Matt Cockrell, tomorrow at 1:15. He will present the work he has done with Sting on the Pulpino core. Thank you very much.
Hello, I'm Boris Shingarov at Labware. I'm concerned with the adoption of RISC-V beyond things like embedded microcontrollers. If you wanted to go to data centers, mobile devices, and you name it, we cannot just stick with only C and assembly. We need dynamic languages. People are asking for Java, for Smalltalk, for Python, for Ruby, you name it. For example, people are looking for a real Java VM, and by real I mean robust, high performance, modern, efficient, and so on. OTI, which is now IBM OTI Labs, has done J9, one of the most advanced JVMs. Two important advances recently happened to that. The VM has been factored to a language-specific and a language-agnostic part. So, for example, the actual compiler that generates the actual code, the actual native code, is completely language-agnostic. The second important advance is that it has been fully open-sourced. So, this poster, the interest is twofold. In the short term, I show preliminary results porting the processor-specific part on RISC-V. The long term is based on existing work that I presented at the last RISC-V workshop in November. We do two things. Well, first of all, we do runtime abstractions such as the one in the OMR. And the second part is there is a strategy for automated synthesis of the JIT backend from the formal specification of RISC-V by machine reasoning, which is verifiable by formal methods.
Okay, I guess that's me. Buenos dias, everyone. My name is Christoph Schulz from Sega Microcontroller from Germany. We're a proud sponsor of the RISC-V Foundation. And yeah, I want to be part of the great success story from the early beginning. That's why we bring our 25 years of experience of embedded systems to this team. And yeah, we come from this embedded world, and we provide a lot of middleware components as development tools, production tools, exactly the rainbow you can see. Everything out of one company, or the one-stop shop, and yeah, proud to be a sponsor. And yeah, our headquarters in Hilden in Germany. And yeah, being a proud sponsor, we want to contribute to the success story of this RISC-V Foundation, and that's why we already ported a lot of middleware components and other tools for this architecture. And we're also here at the tabletop presentation today. Everybody's invited to see the demos of our own RTOS Emboss Embedded Studio, our own toolchain IDE, which also supports now RISC-V architecture, as well as our famous J-Link debug probe. So everybody is invited to join me and my colleague Martin, have a great conversation, and show you some demos and how this looks in real time. Thank you very much.
So I'm Wei Song from RIE, the Institute of Information Engineering from Chinese Academy of Sciences. Actually, RIE is one of the major research facilities in China researching on cybersecurity. And starting from 2016, we have a new group researching on the security side of the computer architecture designs. So this time I bring here a rather simple idea. So we found that much of the userland cat side channel attacks rely on the direct mapping between the virtual addresses to the cat side indexes to launch their attacks. And one of the recent attacks, the ANC attack, utilized this relationship to attack the MMU and bypassing the ASLR production inside major browsers. What we found is actually if they depend on this relationship between the virtual address and the cache set index, we can break this link. So remove these connections. We can remap the cache layout, and then they can't find the right cache set to launch attack. So what we do is relatively simple. We found out that the userland program normally doesn't know the physical address. We just use the physical address as a key to hash the cache index. So therefore, as long as the attacker doesn't know the physical address, they can't actually generate the right cache conflict to ubique cache sets, and the attack probably got failed. So here's what we do. We simply use a part of physical address and hash it with the virtual address and generate a new cache index. And you can see there it's quite simple, just a small change to the cache hierarchy. And we found that as long as the OS constantly allocated random physical pages to virtual pages and disable the large page support for these userland programs, and we increase the difficulty in the cache attacks quite normally. And we implement this on the Boom SoC and find out the performance overhead is quite marginal. So here you can see that performance drop is probably in the 1 to 2% area. Thank you.
I'm Greg Sullivan from Dover Microsystems, and we do cybersecurity. As you probably all can agree, current cybersecurity software solutions don't work, and not only do they not stop interesting zero-day bugs, but they slow down your system and have themselves vulnerabilities that make your system even worse, less secure. So we'll all agree that there needs to be some sort of hardware basis for a solid security solution, and Dover Microsystems is building our CoreGuard product, which is a hybrid hardware IP and software IP solution. The hardware basically orchestrates and guarantees that every instruction that runs on the host CPU is subjected to policy enforcement. The policies, though, are written in software, and so can implement any dynamic analysis. So we have demonstrations of memory safety, stack safety, control flow integrity, any information flow control, and so forth. So we stop entire classes of attacks, and we use a rule cache such that you don't actually implement these software-defined rules on every instruction. So the basic the basic architecture of our system, the CoreGuard IP grabs signals from the host CPU. In particular, we grab some sort of a trace of instructions and reference locations. And for that, by the way, we're talking with Ultrasoc and Sci5 and so forth about a trace interface that we can use to enforce our stuff, even though the original motivations for those additions, specifications might be more debugging. We can also use it for enforcement. And come to the table. I don't have a demo for you, but security demos are always kind of boring. We show you that we can attack a system without our stuff, and nothing interesting happens with our stuff. Thank you.
My name is Trout, and I work for Micron. Yes, the same Micron that sponsors it. Why is a memory company at a CPU conference? Well, at least one good reason is probably about 10 times more transistors are placed on your board to support the memory versus the CPU. It certainly seems like a good place to look for optimizations. And we are actively looking at that. We have some FPGA models that can implement some particular styles of access, such as the straight linear access or the stepping access, and the one on the right there, which is essentially an indirect access where it's going through a table. With that knowledge, the memory can optimize its internal resources and do a far better job of delivering the data to the processor. It can optimize RAS-CAS chains, something that nobody probably in this room other than the memory people even think about. Our internal tests suggest that for some specialized programs, such as sort, we could actually outperform the cache. Sort actually doesn't exist as a problem. You write to memory in one access protocol and you read back in the index protocol. So the entire corpus of the vector processing, all the underlying data movement, could be managed inside the memory. And that will give you significantly better performance. So, this is not your grandfather's memory. That's not me, I don't think. Might be, soon. So if you're interested in figuring out how to use the majority of the transistors that you invest in your product, why don't you come by and talk to us? Thank you.
Good afternoon. My name is Vasily. I'm from Syntacor, and my poster today is about the SCR5 CPU and the SDK based on it. So SCR5 is a mid-range CPU with RV32G instruction set. It's highly configurable. It supports both standard RISC-V extension and custom extensions. So its features list include memory management unit, include virtual memory support, 3 privilege modes, full cache coherency, as well as the atomic extension. So this allows it to run an SMP Linux. So this SCR5 can be configured in single, dual, and quad-core configurations. We've also delivered this SCR5 to our customers in different configurations, and the dual-core configuration has been taped out early this year. So we're expecting the samples in silicon soon. So if you're interested in evaluating the SCR5, we prepared an SDK. So SDK is supporting dozens of standard FPGA dev kits. We can implement you, so we can supply you a pre-built FPGA image and open FPGA project. And as also, we can helping you to migrate to your favorite FPGA board. Apart from this, we can provide you a number of software collateral, including the toolchain with ID and bootloader, SMP Linux, and some software examples. So today we've got a demo. So if you're interested in the SCR5, you're welcome at our poster. Thank you.
Hello, my name is Danny Ibarra, and when you hit the Ys, we're almost done. Okay. My job here today is I've been leading the integration of our security solutions into all our products that are deep and wide. As you know, we're in the enterprise world for both HDD, SSD, client products, consumer products, SD cards, and the like. So my job here is not to go into the deep dives that you guys are going into, but mine is to try to really break it into 2 pieces. One, lessons learned, I'll be talking to things that you need to consider how you can help the next level up, meaning that your products are delivered to somebody, what do they need to be able to do? I'll try to look at it from a whole view, because when we talk about our processes, we think in terms of manufacturing, field, basically cradle to grave on product management. So I'll be focused on that. The second half will be future-oriented, in this particular case, looking at how we can integrate the RISC-V into our security solutions as one of the CPUs in our storage devices. Here's just an example of a quick picture that's excerpt from our presentation, the poster presentation. It talks about the chain of trust, the root of trust, the fact that we do have roots of trust in every storage device as a base, meaning cryptographic module embedded in our SoCs. How does that work against the deployment and all the things that we have to consider with performance characteristics that we need to be able to satisfy security protocols and the like, and also really is manufacturing and key management and all that stuff. So that's what I'll be talking about. And then focus on, here's the areas that we're looking to grow in using RISC-V as part of the crypto subsystem. So that's what I'll be covering.
Hi, my name is Clifford Wolf, and my poster is about RISC-V formal. Don't panic, that's okay, I don't have slides, I just have a poster. RISC-V formal is a framework for formally verifying RISC-V processes against the specification, the formal specification that is part of RISC-V formal. So it's not a formally verified processor. Instead, it's something that you can use to verify your processor formally. And all you need to do is implement the special trace port that I call RISC-V formal interface. The specification that's included in RISC-V formal to verify, hopefully, your processor is itself formally verified against the C code in Spike and the Haskell code in the MIT formal spec. And when you have a tool that can do model checking on anything that's Verilog or VHDL, then you can just use RISC-V formal as this. It's all open source. But if you don't have such a tool, then no worries. I also wrote the open source model checker that can do the same thing. So if any of that is something that seems of interest to you, see me at my poster. Thank you.
Hello everyone. I am Ekaterina from Syntacor. And today we are going to show you our samples with our RISC-V cores. One of them is a system on a chip with a high-performance MCU called SCR3. Another two are FPGA-based SDK samples. One with our efficient APU called SCR5, and another with open source minimalistic MCU called SCR1. All of them with running software, Zephyr, Linux. Also we have Eclipse-based IDE. That's it. Welcome to our demo table. Thank you.
Yeah, hi, it's me again. And actually, you've got too many slides here because they lost the presentation. So you've got a larger slide set than should be, but we'll see. So I'm going to talk a little bit about Empirus here. So the first thing is we're a commercial solution. Oh, I have to talk through this, don't I? Commercial solution, 10-year-olds, profitable. We built a very fast simulator. That's the one thing you should know. Thousands of MIPS. I showed you a video earlier of booting SMP Linux. And actually, I was just playing on my machine because somebody asked me, I made a glib comment earlier about 4,000 cores. Well, I just ran 8192 running dry stones on my laptop, and it worked while I was just watching the previous presentations. So it's a pretty fast simulator. And we build models. We make them open source through actually an Apache license. It's a closed source simulator, We have the RISC-V, actually 26 different models of the sort of generic 2.2 and 1.10 specs, and 2.3a and 1.11. But also we have models of the Andes with their extension V5M instructions there. We have models of the Sci-Fi microassembly as well. And then we have obviously the other vendors as well, which is where we've been making money for the last 10 years. But we also have all the peripheral models as well. And not only do we have the models, but we have what we call extendable platform kits. So these are models of a whole platform, which includes the other models in there. And so you can actually run Linux and things like that, and FreeRTOS. But the great thing is they come as source, so you can extend them. So you can add your own models if you like, use the models out of the library and build it. And we also build tools that run with these models. So it's a simulator we sell, but we also have all the debug, verification, analysis, and profiling tools on top of that. And it's very much OS aware. So instead of booting Linux and looking at 1 billion instructions, you can watch the 600 or 700 tasks and functions as it runs. So it's very easy to actually use for porting software. And our customers really are focused on software development, though we do have a couple of architecture licensees of one of the other processor vendors that use us to drive their performance simulation tools, because we have complete introspection dynamically of how all the instructions are using all the resources in the processors. And really the third thing is, one of the challenges with RISC-V is that you can extend it in any direction you like, which is good and bad. And in terms of our simulator, we have a model of the basic what do they call them, standard extensions, which you can configure. But we also have the ability for you to extend that. So we, in building our model and working with customers, we built our own internal sort of simulation test suite for it and a compliance suite, so we actually can test people's RTL to ensure they're compliant to our model and to the specification. But also we have the ability to extend it so that you can extend the and add to the instructions by using an extension library rather than fiddling with the source of the original model. And you get full debug, trace, and analysis from that. And what we're going to demonstrate up here is actually the custom instructions that we've been working with a company, Cerberus, a security thing. And actually, it's not 5 instructions. It's just a few of their instructions that we've put in there. And they've provided this. And actually, the demonstration we have is where they've extended, we actually extend the Sci-Fi U540 model running Linux, and we actually run some crypto code inside as an application in Linux. And of course, they're using crypto instructions which don't exist in the Sci-Fi course, so we add those to them, and then you can debug and single-step the application within Linux as a demo. So that's what we're going to be showing outside in a few minutes, and thank you very much.
So you might remember me from before. Yeah, we'll be showing the setup I was talking about with Reno, the open source but commercially supported simulator. And we'll be focusing on the multi-node use case with both 64 and 32-bit nodes. We have Linux, we have Zephyr. I guess these keywords pop up very often here. And they are all interconnected, they're all communicating. We can debug them, we can use all the tools I've been talking about, all the functionalities I've discussed during my talk. We can actually demo them to you. So please come see our demo. And that is, of course, not all, because yeah, that's what it's going to look like. Of course, it's going to move. And then we also have another demo on our table, because it's big. This is a really cool project we did together with Thales. It's an application for the space domain where we built a fault-tolerant RISC-V-based system running Zephyr, managed from Linux. It's a pretty cool setup. We're running it on some UltraScale Plus hardware of ours. So, if you're interested in the simulation stuff, see the left side of the table. If you're interested in the FPGA, prototyping, proof of concepts, and so on, you're probably more looking to see this. And we can, again, demo this to you and kind of explain what goes on between all these blocks here. I won't get into detail right now. Thank you.
Okay, having an ISA is not enough, right? And implementing that ISA in a core is also not enough. You've got to be able to run software to make it useful. And software, as we all know, is full of bugs. So you need to be able to debug those bugs out of the software. So this is okay for classic runtime debugging. So that's also not enough, because in a real system, in a real complicated system, you want to be able to debug code running on the software, on the core real time. So for that, you also need instruction trace at least. That's not enough either, because in a real system, you'll have, I hate to say this, in a RISC-V world, RISC-V isn't the only core that there'll be. There'll be other cores too, because real systems will have many different cores fit for purpose. So you've got to have a system that can, a mechanism by which you can run, understand how the software is behaving in multiple cores in real time in the field. So that's not enough either, because you want to also observe not just cores software running, because softwares interact with other bits of hardware in the SoC, and that is what makes the system work. Now, if you can't have visibility when something goes wrong just outside the core, then I think you're pretty stuffed. So what UltraSoC does, and will show, is what's provided in these blue blobs. So we provide silicon IP, which will help with classic debug, your boring source level debug. We'll show instruction trace on both Sci5 cores and Andes cores. And then also we shall provide means of debugging, in this case, ARM cores at the same time. And we should be able to show system behavior across the interconnect in real time. And it will look like this in our Eclipse IDE. So we'll have the classic source level debug on the left-hand side, instruction trace, compressed branch instruction trace decoded in the middle, and then you get system-wide bus transactions, both in textual form and graphical form. So do come and see our demo. Thanks.